Greetings, students. This is the first set of notes in the minerals unit. It's called ES 4.1, What is a Mineral? And here are some people walking in a cave full of giant quartz crystals. Those are minerals. One thing I want you to think about when you see this image is that it's warm down there. Crystals grow larger when it's warmer. What is a mineral? Minerals are solid substances made from pure elements or compounds. Rocks are made up of combinations of one or more minerals, but rocks are not minerals. Suppose you found a solid substance on the ground. How would you determine if you were looking at a mineral? Zinc, S-I-N-C-C. A mineral must have 5 characteristics abbreviated as Zinc, S-I-N-C-C. It must be solid, inorganic, naturally occurring, with a chemical composition and crystal structure. We'll talk about what each of those means. Solid cannot be a liquid or a gas at room temperature. Inorganic, not living, nor derived from living things. N is for naturally occurring, that's made by the earth, meaning that this olivine outcrop that the arrow is pointing to, that would be there whether or not people were around, or any life on earth was around for that matter. Naturally occurring, happens in nature. Chemical composition means only certain atoms are present, and it can be written in a chemical formula, and therefore it's a pure substance. Peridot has magnesium, silicon, and oxygen, and only those atoms are present. If there were other atoms present, you'd have a different mineral. The first C is for crystal structure. The atoms arrange themselves in a recognizable geometric pattern. Take a look at the top. You've got cubic. That is the simplest one, and it gets more complicated from there. But if a mineral has cubic crystal structure, that means its atoms arrange themselves into cube shapes, but then the mineral itself will also arrange itself into a cube shape at the visible level. Minerals can be elements like gold or aluminum, or minerals can be compounds made up of 2 or more elements. One of the most abundant minerals on the planet is quartz, abbreviated as SiO2. That's 1 silicon atom for every 2 oxygen atoms. Gemstones are also minerals. Rubies are the red form of corundum, also known as aluminum oxide. 2 aluminum atoms for every 3 oxygen atoms. This is a picture of sand in a microscope. Now, not all sand would look like this, but at this particular beach, you've got little pieces of seashells, you've got different minerals, you've got probably bits of sea glass and plastic as well. But sand is going to be primarily silicate minerals, because silicates are the most abundant minerals on the planet, like quartz and feldspar. So what is the difference between rocks and minerals? Minerals are a pure substance. Minerals can be elements or compounds, and rocks are made of minerals. But rocks are made up of 2 or more minerals, and therefore it's not a pure substance. Examples of minerals as elements, we have gold, the chemical symbol is Au, aluminum, the chemical symbol is Al, and sodium, the chemical symbol is Na. Sodium by itself is a metal, but when you combine it with chloride, it becomes sodium chloride, which is a compound that's also a mineral, table salt. Calcium carbonate is a mineral, CaCO3, and sodium silicate, Na2SiO3. So why do minerals matter? Minerals have all kinds of uses, from construction to electronics to medicine. Minerals are important to human health and well-being. Calcium, potassium, sodium, and zinc are all part of a balanced human diet. We do need to eat some metal in very trace amounts in our food. The Earth's crust is made up of elements, and these elements make up minerals. The most abundant minerals in the crust are silicates, which contain silicon and oxygen. Over 90% of Earth's crust is made up of silicate minerals. Common silicates are quartz and feldspar. This pie graph shows the elemental abundance. So oxygen is actually the most common element in Earth's crust. And as you know, oxygen is a gas when it's by itself, but this oxygen is bonded to silicon and or other elements. How do minerals form? Minerals form under a variety of conditions, including the cooling of molten rock, the evaporation of liquids, and the cooling of a supersaturated solution, like we did in class. Often, mineral formation involves high pressure and temperature. As the mineral forms, the atoms arrange themselves into patterns. The patterns of the pattern of the atoms gives the mineral its specific crystal shape. Temperature changes can occur quickly or slowly. When minerals cool slowly, meaning the temperatures are higher, the crystals get bigger. Like in this picture we looked at before. It's warm down there, so the minerals are never really cooling off completely, and they're just growing and growing and growing. When mineral cools off quickly, that's a low temperature, the crystals are smaller. Further explanation about the defined chemical composition of minerals. Defined chemical composition means that there are only certain atoms present. For example, quartz is SiO2, that is one silicon atom paired with two oxygen atoms. If different atoms were added into this compound, you would have a different compound, and thus a different mineral. Every mineral can be assigned a unique chemical formula based on the elements it contains. In silicate minerals, which are the most abundant in Earth's crust, silicon and oxygen are often bonded to metals. For example, the mineral magnesium silicate or pyroxene is found as MgSO3. That should actually be MgSiO3. Oops. Got to get back to where we were. This formula contains a silicate anion, that's the SiO3 part, bonded to a metal cation, that's the magnesium. And it looks like that, the picture in the bottom right corner. Every chemical compound, and thus every mineral, is made up of atoms bonded together. The arrangement of electrons for each element causes them to bond in particular ways, which causes the visible pattern, or crystal shape. Depending on the elements, the bonds can be strong or weak. Weak bonds are broken more easily than strong bonds. When a mineral breaks along weak bonds in particular places, it's called cleavage. For example, halite or table salt breaks into cubic shapes. So this is what salt looks like under a microscope. If you had a big piece of salt, it'd be a big cube. And if you broke that big cube with a hammer, it would break into smaller cubes. And when you have salt in a salt shaker, it's actually tiny little cubes. And that's because that's the crystal shape of halite, which is table salt. Mica, which we've looked at in class, has flat cleavage. That's due to the weaker bonds between the flat layers. And there's a bunch of crystal shapes: isometric, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. You don't have to memorize any of those. It'd be good to remember that cubic is a crystal shape and that mica has flat cleavage, and that's its crystal shape. But as far as memorizing all these big words, don't worry about that. Just know that there is a unique crystal shape. And that's it.